For electric circuits, you need to be able to define potential difference as work done per unit charge. It's easy to remember that because this equation is on your information sheet. V is equal to W over Q. So what is potential difference? It's the work done per unit charge. Easy as that. Current is, this formula is also on your information sheet. I think it might be written as Q equals IT, but it's the same thing. I is equal to Q over T. So what is current? It is the rate, because we're dividing by time, of flow of charge. So it's the rate of charge moving. So it's the rate of flow of charge. So you need to have that definition in your quiver. Ohm's law states that the current through a conductor is directly proportional to the potential difference across a conductor at a constant temperature, which means that resistance is equal to V divided by I. Notice the constant temperature is important. What is resistance? It is defined as a material's opposition to the flow of an electric current. If my resistors are connected in series, I just add them up. If they're connected in parallel, it's 1 over R1 plus 1 over R2 plus 1 over R3 equals, sorry, this is a mistake, 1 over R parallel, and then we can solve for R parallel. Don't forget to flip at the end. Electrical energy is, remember what energy is? It's work done. So work done is energy transferred, and we can say electrical energy is work done, which is power times time. We measure electrical energy in joules. Power is equal to potential difference times current. It's also equal to I squared R, and it's also equal to V squared over R. Good news is that these equations appear on your information sheet. Bad news is when I want to do it as work done, they do not appear on your information sheet. So you need to kind of derive them. Not that tricky. Work done is equal to power times time. So I take the power number and I times it by time. And I take the power and I times it by time. Take the power and I times it by time. Simple as that. So you can easily derive those. We need to know what a kilowatt hour is because that is how we measure energy. It seems like it might be power because of this watt bit over here, but it's not. It's kilowatts times time. Kilowatts times hours. Power times time, which is an energy thing. 1 kilowatt hour is 3,600,000 joules. You're going to have to be able to calculate the cost of electrical energy as well. How much does it cost to get there, to get electricity in our homes? Internal resistance is the resistance of a battery, and EMF is defined as the total energy supplied per coulomb of charge by the cell. All of these are only useful, well, you need to know your definitions, but in as far as we can apply them. So I'm going to look at the 2 examples that were in your pack of revision material, and let's see if we can apply all of this information to the... Right, so the first one over here, we've got a circuit shown below, and we've got resistance, and the switch can be ignored, or the resistance of the switch. The voltmeters have high resistance, the battery has got internal resistance. When the switch is open, the voltmeter reads 9 volts. That means that the EMF is equal to 9 volts. That's what that is telling me. When the switch is closed, I've got a current reading of 600 milliamps. But take a look. Remember how we highlighted? Pretend the switch is closed now. So I'm going to go all the way around till I hit a resistor. I'm going to go along until I hit a resistor, and along until I hit a resistor, and the other way, the same story. You can quite clearly see that those 6 ohm resistors are in parallel with one another. They are identical resistors, which is good news. That means that I can put another 600 milliamps on that branch. When those 2 branches come together, if I had an invisible ammeter over here, it would be 1,200 milliamps, which is actually 1,2 amps. So we need to keep all of that in mind. And then let's see what the questions ask us. Firstly, calculate the total resistance in the external circuit. Well, how do we go about that? We know that we've got a parallel network. 1 over R parallel is equal to 1 over 6 plus 1 over 6, and therefore that is equal to 2 over 6. And R parallel is equal to 3 ohms. We've then got a series system over here, so I need to add that to the 3 ohms. 3 plus 4 is equal to, and is that everything? Yes, 3 from the equivalent resistance of the parallel network, and 4 from the series. And we land up with 7 ohms of external resistance. What's the internal resistance of the battery? Okay, well, we happen to know the current strength, so we can work out the total resistance. R total is equal to the EMF divided by the series current. So if I know, what's the total potential difference? 9. What is the current on the main branch? 1, 2. And I land up with an answer of 7,5 ohms. Well, 7 of those ohms come from the external circuit. What about this 5? Obviously, the internal resistance is 7,5 minus 7, which is equal to 0,5 ohms of internal resistance. Then if we take a look at 11.3, calculate the reading on V1. Remember, now the switch is closed, so it's not 9 volts anymore. 9 volts was when it was open, it was an EMF. So we now need to consider a slightly different number. Let's see what happens. If I have got current strength, I want a potential difference. Potential difference is current times resistance. What current? The main branch current times what resistance? If I want that voltmeter, I need to use the external resistance, which is only 7, and that turns out to be 8,4 volts, which means that 0,6 volts has been lost in the process. Carrying on, explain why the voltmeter reading changes when the switch is closed. It is because the internal resistance used 0,6 volts to drive the current through the battery. The 4 ohm resistor is now replaced by a 4 watt light bulb, and the reading on V2 is now 2 volts. So I now have some information that involves power and potential difference. They asked me to work out current, so I can do that easy enough. I can say that power is potential difference times current. 4 is equal to 2I, and I turns out to be equal to 2 amps. Quite convenient. Explain why the reading on voltmeter 1 is going to decrease when that 4 ohm resistor is replaced by a 4 watt bulb. Let's look what's happened to the current. 1,2 amps has changed into 2 amps. That means more current is trying to go through the battery. When more current is going through the battery, there will be more lost volts. And for that reason, we're going to find that if more lost volts, there's less potential difference for the external circuit. I think we need another color. Don't know if that's much better. For external circuit. So that is why that goes down. Electricity is charged in a unit called kilowatt hours. Let's just make ourselves some space. Convert 6 times 10 to the power of 5 joules into kilowatt hours. So it's going to be equal to 6 times 10 to the power of 5 divided by 3,600,000 joules, and I land up with 0,17 kilowatt hours. So that's always how you go about converting between the two. A computer is left on for 18 hours a day, drawing 20 watts. Calculate the annual cost. So first we're going to say that work done is equal to power times time. What is the power? The power is 20 watts, which is 0,02 kilowatts. Remember, we want to be in kilowatt hours here. The time is going to be 18 hours per day, and it's for the whole year. The annual cost, 365 days of the year. That turns out to be equal to 131,4 kilowatt hours. This was all hours. And therefore, what's the cost going to be? The cost is the total kilowatt hours multiplied by how much does 1 kilowatt hour cost, 1.20 Rand, and I find that I get 157 Rand and 68 cents.